So for all projectile problems, I think you should take a few minutes to consider what you're being given in the problem. This problem indicates that a low-flying plane drops a package from 550 meters above the ground while it is in level flight at a speed of 120 meters per second. So plane, package, level flight, which means the velocity of the plane isn't going up or down, it's just going side to side. They say that the plane is 550 meters from the ground. And they ask, how far from the point of release will the package land along the ground? So if this is the point of the release, they're asking us, how far along the ground will the package take to reach the ground? I think we can probably all agree that the package is going to do something like this. All right? It's going to drop. Now, there's a bunch of things here, but there's really not that much to consider. One of the things I told you guys from the beginning is that when you're doing these problems, organize yourself. This isn't new. Put it on the board and we talked about it, but come up with some organization. This is all the information that's going to be given to you in some form or another. And in setting this up, you're also providing yourself with a way of getting organized. So you can't say one of those, I didn't even know where to start. You know where to start, draw a picture. Step 2, write out this chart. Step 3, try to populate the chart with the information you've been given. Now, there's not a surprising group of information here. We have an acceleration in one dimension and no acceleration in the other. That's why these numbers and these placeholders are the way they are. Now you have a group of information that was given to you in the problem. You have to find out where these go. There's no accidents here either. I mean, it's not that hard to figure out. For example, 550, there's only 2 places where it can go, right? Do you understand why that's true? Because if you don't understand why that's true, you're not paying attention. You're paying attention to something else. But there's only 2 places where something in meters can be placed that would make sense. Either delta y or delta x, because those are the only 2 that are displacements. Those are in meters. If you think that number can go someplace else, you haven't been paying attention. So where would I place that? What makes the most sense? Go ahead. I think so too. I don't think that it's going sideways 550 meters. I think it's going downwards 550 meters. So yeah, I'm going to place it there, 550 meters. This is a vector quantity, so I should probably make a decision about whether upwards is positive or upwards is negative. What would you guys like? Well, I had 3 people say things. Doesn't make a difference to me. Do you want downwards to be positive? Yeah. Okay, downwards is positive. Upwards is negative. That means it fell downwards 550 meters. Now, in populating this chart, you need either 3 pieces on this side or 2 pieces on this side. That's how these problems work. So populate the rest of the chart with what's been given. I'm going to give 60 seconds before I start calling names. Where's 13? Where's seat number 13? It's got to be that table, right? Why don't you guys give me one more piece of information? Anything.
Initial velocity in y is equal to 0.
I think you're right. The plane's not going up or down, so the package is not going up or down at the start, so initial velocity is 0 here. Excellent. Let's see what else we got. Seat number 22. I think that's you guys. Okay, I'm going to use 10, if that's okay. But yeah, 10 meters per second squared. And I have to check whether it's, we know it's downwards, and we've made downwards positive, so I'm going to make this one positive. Now, we have 3 pieces here, so we could just start a problem, except there's another number here we haven't placed. And I'm pretty sure almost every number is going to have a place here. So let's see. Person in seat number 6. So that's this table here. Can you guys tell me what to do?
The velocity in x direction is 120.
I think so. The plane's in level flight. That's the horizontal velocity. So I'm going to put the 120 right there. All right. Now, they're asking for where the box lands along the ground. They're asking for this. Every one of these problems is going to have a similar kind of cadence to it, a similar kind of rhythm. So you're probably going to be solving for t on one side and using it on the other. Because remember, this still represents the same event. The package went sideways while it was falling to the ground. So the time it was falling to the ground is the same as the time that it took to go sideways. So you pick a motion relationship. You're supposed to have those suckers in your head. If not, I'm sure you have them in your notes. I'm going to pick one that doesn't have final velocity in it. This will probably do the job, won't it? It's got everything in it except for final velocity. It should help me get the time. So I'll populate it with what we were given. This part is all plug and chug. It's all stuff you've already done. So you're not going to get a whole lot of patience from me. You should be able to do this without too much difficulty. So there we go, 10.5 seconds. Now I would keep a certain number of decimal places between your work here. I think it's best that, remember this is the time, so as many decimal places as you can reasonably keep between steps will probably work here. But this means this is 10.5 and this is 10.5. Whatever time you give for the vertical is the same as the time for the horizontal. They are the same event. Now you have to figure out delta x, but there's only one relationship over here. Delta x equals Vx times t. So again, not a lot here. 120 times 10.5, and I bet you get pretty close to the answer there of 1259 or whatever. All right, we're not going to spend a lot of time. This is the same stuff over and over again. So skip on down to question number 4, because question 2 and 3 are exactly the same. All right, ready? All right, so let's roll the dice here. 16. I think that's that table, right? Give me one piece of information that's in this problem.
Delta y would be 1 meter.
1 meter, and I'll let you make this decision. Do you want up to be positive or up to be negative?
Negative.
All right, so up is negative. That means downwards is positive. That makes the 1 meter positive or negative?
Positive.
Positive. Excellent. Thank you. Let's see. 27. Where's that? Can you guys give me something for this chart? Starting velocity for y would be 0. Sure, the table is horizontal, so the car, when it leaves the table, is moving up or down, so I think that's a good choice. Excellent. So 32, where's that? Oh, it's that table. How about you guys? Can you guys give me something? Delta x 4 meters? I think you're probably right. It's the only other displacement up there, and if 1 meter's in the right place, that one has to be in the other place, right? Excellent. So we're getting closer. Again, we need 3 pieces here or 2 pieces here, and I'm getting close. I've got 2 on one side, and I'm just saying 1 more over there, and we'll be good. So let's see what else we could possibly get. Where's 28? You have anything else we could use? Sure, what should I put there? 10 meters per second squared, and I'll make it positive because it is downwards. That looks good. It looks like I have enough information to solve what I need for this problem. I think I'm going to solve for the time using the left side, and I'll plug it into the right side. Is there anybody who wants me to continue this, or are we good? Because they're all the same, it seems like to me. Going once, going twice, okay. So I would probably use something that does not have final velocity in it. So I'm thinking, just like before, delta y equals 1/2 at squared plus vy naught times t. I think this is a good place to start. I'm trying to figure out how long it's going to be in the air for. So this will be 1 equals 1/2 times 10 t squared plus 0 times t. This looks like t squared is equal to 0.2, or t is equal to the root of 0.2, which is 0.45 seconds. All right, so now that I have the time, I'm going to use it in two places. Now, this time we're looking for how fast the car was going when it left the table, so we are searching for the horizontal velocity. So I will use delta x equals vx times t, but solve this for vx, which will give me 4 divided by 0.45, or 8.9 meters per second. So pretty fast for a Hot Wheel car, but it's just a little throwaway problem. Now, all of these problems I call type 1 all have the same trick in them. That trick is that the initial y velocity is 0. So let's skip to maybe one of these type 2 problems where things change a little bit, where you actually might have to think a little bit more. Because the other ones all have the same kind of gotcha. Let's see if this one has a similar gotcha. We're going to do number 1. And I want to make sure we try and finish this. So I want to get it set up for you, and then I'll see what you guys can do with it, all right? I'm going to start by reading the question. It says a football player can punt a ball at a speed of 30 meters per second and at an angle of 77 degrees. I think I spelled some stuff wrong, but I think we know what we're going for. How far down the field does the ball travel? I'm going to draw a quick picture of that. So field, football player, football, punted at an angle of 77 degrees and a speed of 30 meters per second. I think we can probably all agree the ball goes up and back down. We want to know where the ball lands downfield. I think, again, we're dealing with something like this with vertical and horizontal. It has all the trappings of a projectile problem. Delta y, vy naught, vy, a, and t. Delta x, vx, and t. There's a difference here, and I think you know what it is. We have a launch velocity and a launch angle, suggesting we're probably going to have to use vx equals VL cosine theta, and Vy naught equals VL sine theta. Like we talked about the other day, this object is launched so that it has both a horizontal component and a vertical component, right? It's launched with both. Now, we're given the vector, 30 meters per second at 77 degrees, but only part of that velocity is being acted on by gravity. Part of it's not. You have to break it up into its components, which usually means placing the velocity in like this, making your triangle, and figuring out what your opposite and adjacent are. All right, I'll give you a few minutes, but there's also a trick in this question. You need to figure out what it is. So I'll call on 3 of you in a minute. Let's see what we can get together for this one. So let's see. Person number one, can you give me anything that I can use here? We don't have person number one, so we'll use who's ever at the front table.
For the initial velocity, we got 1.57 for vertical.
1.57? I don't think so. Don't think there's a chance. Nope. But what did you try to do to get that?
So I did the sine of 177. And then I multiplied that by 30.
By 177 or just 77?
By 117. Oh, I did 117.
Okay, so yeah, I do think for the initial y velocity, we can get the speed as 30 times the sine of 77 degrees. I don't think it's going to be what you said, but I think it's going to be more like 20 something.
Oh, because I thought that was a 177.
It's okay. I'm just going by what's in the problem, and you know, it might say 77 there. So what do I get? 24? 29? 29.2. All right, 29.2 meters per second. All right, let's see if we got another table to give us something else. 30. I keep calling the table that has nobody there. Let's slide to the left. What do you guys got? Anything for me?
For BX, I got 6.749.
6.749. All right. Again, meters per second. How about we make a decision? Do we want up to be positive or up to be negative?
Up to be positive.
All right, so somebody said up positive. Great. Do we want the right to be positive or the right to be negative?
Positive.
So if we're going to make those choices, that makes this one positive and this one positive. Again, we need 3 pieces here or 2 pieces here. We are not there yet, so we need something else. Let's see. 24. Where's 24? Can you give me any other piece of information that we haven't used yet? Yeah, I think the acceleration will be 10 meters per second squared. And are we going to make this one positive or negative? Actually, we made up positive, so we'll make this one negative. I know the last time we did it the opposite way, but somebody called out positive for up this time, so. We've used everything that's in the problem, but I still think there must be something else. Can somebody come up with the thing that we need here? Because there's got to be something. Because we need one more piece of information. Go ahead.
Would the final velocity of v of y would be 0?
Actually, I would love to say that would be true, but no, it won't be. Vy will be 0 when it makes it to its maximum height, but when it hits the ground, it'll be moving. Go ahead.
The displacement is 0.
Which one, x or y?
Y.
That's right. It lands at the same height that it was launched. So delta y is 0. Remember, it goes up and down. So the y displacement 0 because it's landing at the same height. Everybody see where that comes from? So if you launch something on level ground and it comes back to where the height it started at, then you make your y displacement 0. Now, again, type 2 problems. I've listed them here and I've separated them. Type 1 problems, the initial y velocity was 0. Type 2 problems, the y displacement's going to be 0. So there's a whole bunch of them there. You should try them all. They're all going to have a similar thing, except I don't think you can do the one that says finding the angle. So skip that one. They're going to get a little harder, so start the ones above it. But let's finish this one out real quick because we have time and there's something you should probably see. Using the same relationship, delta y equals 1/2 a t squared plus vy naught times t. All right? I'm just putting in the numbers as we go. I want to be really clear. Even if I distribute the 1/2, this isn't hard, but there are 2 answers. Technically, you're supposed to factor out a t and set them both equal to 0 so that you'll get 2 answers. T equals 0 and minus 5t plus 29.2 equals 0, giving us 29.2 divided by 5, 5.84. There's two answers, but only one of them is necessary. We asked the math to tell us when it was on the ground. It was on the ground at time 0, of course, that's when it was started, and it was back on the ground 5.84 seconds later. Not a big surprise. Again, that means 5.84 seconds here, 5.84 seconds here, and now you have a pathway to figure out your answer. Delta x equals 6.75 times 5.84. I bet you get about 39 meters. Okay. So